Okay, in this video, we are going to talk about a concept known as Le Chatelier's principle. Okay? And so Le Chatelier's principle starts as follows, right? So let's say we have a system. We use this. Say we have a system that is at the start at equilibrium. Okay, using this analogy. Okay, so starting off, we're at equilibrium. If we then do something to this reaction that and remember what equilibrium is, just as a reminder, equilibrium is when the forward rate equals the reverse rate. But if we do anything to a system at equilibrium that changes one or both rates, the system will shift to reestablish equilibrium. Okay, so if we do anything to a system that's at equilibrium that changes one or both rates, right? So if we do something that makes the forward rate faster or slower without affecting the reverse rate, or we do something that makes the reverse rate faster or slower without affecting the forward rate, or if we do something to the system that changes both rates but changes them differently. In other words, anything that causes the forward and the reverse rates to no longer be equivalent, right? Then the system, you've knocked it out of equilibrium. The system will attempt to reestablish equilibrium by shifting, consuming more reactant, forming more product, or forming more product, or forming more reactant and consuming more product to reestablish, to get back to equilibrium. And so this is why I like this kind of ball analogy here, right? We have the ball at the bottom of our valley, and it's just going to sit there if we don't do anything. But if we do something that causes it to either push the ball up the left side or the right side, okay, then the system, so we are doing something that causes Q to become less than K, right? So we made Q decrease or we made Q increase relative to K. Then the system in this case, it's going to shift to the left to return the equilibrium because the ball is going to roll back down the hill again. Let me draw that a little bit better. All right. So if you do something to push the ball up on the right side, then it will shift left to get back to equilibrium, meaning it will be forced to increase the concentrations of its reactants and simultaneously decrease the concentration of the products until Q equals K again. So that's why it's shifting. A shift in a direction means increase the concentrations on the side it's shifting to, decrease the concentrations on the side it's shifting from. Because rolling the ball up the right side of the hill means that your relative rates, so your rate forward and your rate reverse, you have done something to make your reverse rate faster than your forward rate. And there's multiple ways to do that. We could do something that causes the reverse rate to get faster without changing the forward rate, or we could do something to decrease the forward rate while the reverse rate remains constant. Either way, by making the mismatch in such a way that the reverse rate is now faster than the forward rate, that is why it shifts left, okay? Because the reverse rate is faster than the forward rate, so you would observe it forming more reactant and consuming more product, even though the cycle's occurring, it's just occurring faster in one direction than the other. So it will appear that all that's happening is reactant concentrations are going up and product concentrations are going down until it reaches equilibrium again. Same thing on the other side. If we do something to roll the ball up the left side, making Q less than K, and so in terms of rates, if we do something that causes the forward rate to now be greater than the reverse rate, and again, that could be making the reverse rate faster without affecting, making the forward rate faster without affecting the reverse rate, or it could be something to make the reverse rate slower without affecting the forward rate, or it could be something that affects both, but it increases the forward rate more than it increases the reverse rate, or it decreases the forward rate less than it decreases the reverse rate. All of these will lead to the equilibrium shifting right. Okay, so over here we had shift left. Okay, and here we have shift right. And again, so in this case, to shift right, that means consumption of more reactants and formation of more products to get back to equilibrium. And note, after it reestablishes equilibrium, the rates will be equal again, but the absolute rate, so the relative rates will be equal, but the absolute rate will be faster or slower than what the forward and reverse rates were at the previously established equilibrium. Okay, so let's see what causes shifts to the right versus shifts to the left. Okay, move this up. Let me delete that. Erase these. All right. This up here. So let's look at these scenarios. So what are things that cause the forward rate to be higher than the reverse rate such that the system will need to shift to the right to reestablish equilibrium? Well, if I add reactant to the system, that will cause the forward rate to increase without initially affecting the reverse rate. Okay. And so to offset that, the reaction will have to decrease the concentration of all reactants and increase the concentration of all products because the forward rate is now faster than the reverse rate. And note, it's not necessarily like conscious in doing that. It's just statistically, if there are more particles of reactant colliding than particles of product colliding, and the forward rate is faster than the reverse rate, then it's just based on math and statistical probabilities, right? You're going to be forming product faster than your products are forming reactant. And that's going to happen until the forward rate gets slow enough and the reverse rate gets fast enough, because both are going to happen simultaneously, to reach the new equilibrium rate. Okay? What's another way we could do this? We could remove, right? We could add reactant such that we increase the reactant concentration. We could remove product such that we decrease the product concentration. Well, that would cause the reverse rate to get slower. Again, that leads to a situation where the forward rate is faster than the reverse rate, and again leads to a shift to the right, which again is depicted by, you're going to see all of the reactant concentrations go down and all the product concentrations go up. So that means if we remove reactant and thus make the reactant concentration go down, then that process causes the forward rate to decrease, resulting in the reverse rate being faster, and that would cause a shift to the left, the opposite of what happens when we add reactant. Okay, if we add products such that the product concentration goes up, well, now that change is making the reverse rate faster, which again leads to the reverse process happening faster than the forward process is, and it leads to a shift left, increase in the in concentration of reactants and decrease in concentration of products until a new equilibrium rate is established. So hopefully this is making sense so far. Okay, so what are some other things we can do? Well, so that's what we can do for concentrations. For gases specifically, okay, we know that that is equal rates. So for gases, we have some additional considerations that can lead to the rates becoming unequal. Okay, so for gases, increasing the pressure of a reactant is the same as increasing the reactant concentration, right? So that is the same and will have the same effect as this. And that's only if we increase the partial pressure of one of our gaseous reactants. If same thing, if we were to decrease the partial pressure of a product, well, again, that's going to be the same as decreasing the concentration of a product, which again results in a shift to the right. And so, of course, the opposites apply on the other side. Because whatever goes in one direction on one side goes in the opposite direction on the other. So again, decreasing the pressure of a gaseous reactant has the same effect as decreasing the concentration of a reactant. And again, increasing the pressure, partial pressure of a gaseous product is the same as increasing the concentration of a product. Okay. And all of this, again, just a reminder here, right? PV equals nRT. Concentration is just N over V. Therefore, concentration for a gaseous species is equivalent to the partial pressure of that species over RT. And so note that's a direct relationship. Okay, now there's another way that we can affect, and this is special to gases. Okay, so remember that the concentration of a gas, so remember that the concentration of a gas is equal to the moles of that gas divided by the volume in liters of the flask, the vessel that it's in, right? So the volume of your container, because remember, gases fill the entire container. Remember, the concentration of a gas is just the number of moles of gas in that volume. And if we want it to be molarity, then it's got to be, we have to have moles of gas divided by the volume of the vessel in liters. So let's look at what happens if, so let's imagine that we have a vessel here that has a piston. Piston just means we can move one of the walls of our container to increase or decrease the volume of the container, right? So we've got some reaction in here, reactants to products, right, as gases. Okay, so let's decrease the volume of the vessel. Okay, so what's that going to do, right? So if we take this and we take our piston and we squish it down. Okay, so now the volume of the vessel is getting smaller, but the moles of our gas are constant. Then that has the same effect as increasing the concentration of all gases in the container. Okay, if we go in the other direction, if we increase the volume of the vessel, and again, our moles of our gas are constant because we're not adding or removing any gases to or from the container. Let me extend this up here. Oops. Okay, this will have the effect of decreasing all of our gaseous species concentrations at the same time. Okay, so we can see now that changing the volume of a container affects the concentration of any gases within that container. Now, note that won't affect the concentration of things in liquid because things that are dissolved in a liquid, liquids are incompressible, right? So this only applies to gases. Anything that's a gaseous component of a reaction, its concentration and only its concentration will be affected by a change in the volume of the vessel. Okay? So this leads to the following consequence, and that is smaller volume for our container, our vessel, means more collisions between particles. You learned about that previously, right? And so larger vessel means fewer collisions. And let me add per unit of time. So in other words, like collisions per second. So fewer collisions means decreased rate. More collisions means increased rate. And here's another thing that's unique about gases. Changing the volume of a container that has gases on both the reactant and the product side will lead to both the forward rate and the reverse rate change if everything's a gas. In other words, we are either making all of our reaction rates with associated gases slower, or we're making all of them faster. The difference here is like making the vessel bigger, meaning there's more room for the particles to spread out, and thus they collide less often per unit time. So our rates all go down, but the forward and the reverse rates are not going to go down equally. Okay? So I have a way of like, so let's say we have a reaction that has only gases in it. Okay? Actually, well, let's just look at a series of them. Okay? So this really should have been a separate video, but I'm already here. Let's look at 3 scenarios. Okay? So let's look at the first scenario. And for each of these, they're all in some flask. And for all three separate examples, we are going to do the following. If we increase the volume of the flask, what will happen? Right? And so our options are going to be shift left, shift left, shift right, or no change. So that's what we're going to try to predict for each one. Okay, so let's look at our first scenario, right? The first thing we're going to do to figure out which direction this is going to shift, or if there's going to be any shift when we increase the volume of the flask. So remember, an increase in the volume of the flask leads to a decrease in the concentration of any gases that are there. So we have a gas here, and the concentration of this gas is going to decrease due to us making the flask bigger, right? And so this is a product, right? This is a product. And so since it's the only gas, and it's on the product side, right? Um, remember, decreasing the concentration of a product causes the reverse rate to be slower because now the CO2 particles collide less often. So now the reverse rate is slower than the forward rate. And so that's going to cause a shift to the right to form more product and consume more reactant. So this is going to shift to the right in this case. Okay. Hopefully that makes sense so far. Let's look at the next example. Okay. So again, right, we're increasing the volume of the flask. We've got this gas here and this gas here. And so in this case, since these are the only gases, we are simultaneously decreasing the reverse rate and we are decreasing the forward rate. So how do we know which direction it's going to shift? Well, we have to pay attention to our coefficients. N, right? N for our products is 1 mole of gas. On our reactant side, and that's per reaction, per mole of reaction, 1 mole of SF6 is formed. On our reactant side, we have 3 moles of gas. Note we're ignoring the sulfur because it's not a gas, so it's not going to be affected by changing the volume of the container. So what this means is by decreasing the rate on both sides, one of these is going to be affected more than the other. Okay, so increasing volume, decreasing concentration. And I have just a little mnemonic device to help if gases on, actually, you don't even need to do if gases are on both sides. So if volume is made big, so we've increased the volume. I like doing things in caveman speech. Shift big side. Okay, so what does big side mean? The side with the larger N gases, right? That's what big means in this case. So if make, actually, if make V big, then reaction will shift to the big side. If make V small, then shift small side. And so what does that mean? That means the side with the smaller moles of gas coefficient. So let's apply this over here. And it has to do with both of the rates. So by making the volume bigger, both the forward and the reverse rate are becoming slower, but they're becoming slower to different degrees. Okay. And it's complicated, but using my caveman speak over here, using the caveman speak, since we are making, right, since we are increasing, so make V bigger, so shift big side. And so what's the big side? This side's the big side. So that means for this reaction, we're actually going to get a shift to the left in this case. Okay. Now let's look at this last one. Both reactants and our singular product are all gases. Okay. So note we've got a situation now where all of these concentrations are going down, and thus all of the rates are going down. However, we need to look. So N on the reactant side, we add up our coefficients for any species that are gases, 1 and 1, that's 2. N on the product side, we add up our coefficients of anything that are gases, that's 2. They are equal, okay, if N's are equal, then a change in V does not cause a shift. Okay. In other words, we will not see a change because what happens is since we have the same relative number of gas particles on both sides, then changing the volume changes both rates. Both rates change to the same degree. In other words, the forward and the reverse rates are getting slower, but they're getting slower by exactly the same factor. So they're both halved, right? Or if we were to decrease the volume of the vessel, maybe they're both doubled, right? They're both exactly doubled. So no change, okay? So this is how we handle gases with Le Chatelier's principle. We're going to go ahead and call that video here, and we'll talk about Le Chatelier's principle with respect to temperature and catalysts in the next video.